All right, students. This lecture is for Friday, April 12th for the 9 a.m. section that we missed. So I want to do a short lecture that we did in class today later in the day on Chapter 10. Now, a few reminders. One is, remember, you have homework 8, which is due Monday. I sent out an email about this, but there was a typo. Problem 3 should read tin and lead. Okay, so take a look at that. Also, for homework 8, we're going to have a study session tomorrow. That's Saturday from 11 a.m. to 2 p.m. MI 222. Okay. So great. Now let's just remind you what we've been talking about in Chapter 9. Remember, we could take a look at the lead tin phase diagram, for instance. There was two aspects that we focused on with these phase diagrams. So here's alpha and beta. The first aspect is, let's say that I'm just at some temperature down here below this eutectic temperature, right? So the eutectic temperature is right here, T sub E. If I'm any temperature down there, look, you always just put a dot, draw a tie line, do the lever rule. Okay, that gives you all the information we need. It gives you what phases are present, what's the composition of each phase, and the amount of each phase. So down here where that triangle is drawn, we have two phases, alpha and beta, and you can see we have about 70% alpha. So these are the total phases. We have about 70 alpha, or 0.7, and 0.3 is going to be beta phase, right? And you can figure out the composition of each phase too. The composition of the beta phase is like 98 right here, 98. The composition of the alpha phase is about 18.3 weight percent 10. So that's the total phases, right? That always works. But if we want to know the microstructure, remember, I'm going to go to the next slide. Let's draw that same phase diagram. If we're interested in the microstructure, or microconstituents at that same point right here, we have to imagine what happens when we cool down slowly from above. Remember, we drew pictures. We said it's all liquid up here. When you get to right above that line, you could figure out that there's some alpha and some liquid present. It's about half and half, alpha and liquid. But we said below the line, we cool down, we've got alpha, about half of it, but we call it pro-eutectic alpha because it was alpha before we hit the eutectic temperature. And then all that liquid was at this special composition you can see right here in the middle, or near the middle. That's the eutectic composition, so that when we cool it down, it transforms to alpha plus beta mixture, eutectic mix. Now, how much of each? Well, you can see above the line we add about half alpha and half liquid, so that's what we're going to have below the line. Now, why doesn't that agree with what we had on the previous slide? Well, because this was the total alpha and total beta. That's still correct. See, if you come here, we have alpha in the pro-eutectic alpha here, and we have alpha in the mixture here. So the total alpha still got to add up to 0.7. All right. Now, let's proceed to chapter 10. So chapter 10 is on so-called phase transformations. But what it's also really about is trying to controlling the microstructure. Now, let's maybe give you a hint of what we're talking about here and what we're going to get into. One of the themes of this chapter is that most phase transformations take time. They depend on time. We didn't talk about that in chapter 9. We just said that we hold it long enough so that equilibrium occurs. In fact, you have a homework problem on chapter 9 that talks about what does equilibrium mean. Well, it means holding long enough so all the things can settle the way they want. That means diffusion might occur and things like that. All right. Another thing that we can talk about here, and we never mentioned time in chapter 9. In chapter 10, time is going to be a factor. That means how long does it take for these phases to transform back and forth? That's really important. Another aspect of this chapter that we're going to talk about is materials want to reach equilibrium but this is not always practical. Now we can take advantage of that too. Sometimes these non-equilibrium things that can happen can actually help us. So what do I mean by that? Well, let's go to the next slide. Let's talk about, this is related to processing the material. What we're talking about above, all these things, let me just put a big box around this. These two aspects are related to processing. That's like, how long do I put it in a furnace? What do I do to make it non-equilibrium or to get a certain microstructure? That's the processing aspect. So that's what we're talking about in chapter 10. As an example, let's talk about processing steel. If we look at the iron-carbon phase diagram, the portion that we're interested in, most interest, okay, that's this portion, right? We have Fe3C phase on this side. The basis for processing or heat treating steel is to heat up into this austenite region. Here, that's hatched area. So I heat it up into this region here, okay, and then I cool down. One aspect of heat treating is called annealing. That means slow cooling the steel. Well, what do I get if I slow cool the steel? Well, we get alpha and Fe3C, right? This is what we predict from the equilibrium phase diagram. So we can say this is approximately equilibrium. So if I cool really slow, I get what's on the phase diagram. If I cool really fast, that's called quenching. Like I put it in water. This is rapid cooling. This is not equilibrium. In fact, for steels, you take advantage of that. You cool so fast that it traps all the carbon in that austenite structure. It's like a supersaturated solution. All right, now let's talk about phase transformations. So this is a two-step process. Now, what are some phase transformations that we've talked about? Okay, how about austenite transforming to ferrite? That's gamma going to alpha for iron. That was in the last phase diagram. How about liquid going to solid or solid going to liquid? Okay, those are phase transformations. I'm transforming from one phase to another. So it's a two-step process: nucleation and growth. Now, let me draw a picture of this. So here's an example that we're going to go through. This is a liquid going to a solid. Let's say it's iron, like iron. So I melt the iron. So this is iron. I melt it and then I cool it down to solidify it. Well, here we go. It's all liquid here. Then I cool it to below the freezing temperature. So we cool. What happens is, so this is our liquid iron. I have some solid chunks that form. We call these nuclei. Okay, this is like a group of atoms of iron that get together to form a solid. It has like a crystal structure. And if we cool that down more, if we cool it down more, some of those grow. So I'm going to draw those bigger, the ones that were there before. And then we even get some more nucleation. And if I cool it down more or hold it for a longer time, finally the whole transformation is complete. It's all solid. I'm going to draw grains because they're like solid iron grains. But we can say transformation is complete. Now remember that here's the growth aspect. Let me point to this. Here's growth, right? Because on the left they were small nuclei, then they grew. Then we had some new nucleation, right? New nucleation. And finally it's complete. Now the idea in this chapter is, okay, how long does that take? How easy is it? And we're going to talk about how easy it is here in a second. So this is kind of a difficult concept, and we're not going to cover it in too great a detail, but I want to give you a sense of what's in your book. Okay? So we're going to talk about homogeneous versus heterogeneous nucleation. Now, where are we going with this? Well, the whole idea behind this nucleation process is that when we lower the temperature, in our example from before, nucleation of the solid happened in the liquid, okay, right? Well, to do that, some things have to happen in terms of the state of the material, and we're going to describe sort of an energy argument of what happens, okay? So we're going to start with homogeneous nucleation first. Homogeneous nucleation. Well, here's the example is, our liquid going to a solid. So I'm going to draw a picture over here. So here's our liquid, and then we have some solid forming in here. Now, the whole idea is we're going to look at what happens energy-wise that makes this possible. So this is sort of an energy balance. So we're going to look at a free energy argument. And if the energy gets lowered, then the transformation proceeds. Transformation proceeds. Now, well, so what does this mean? So we're going to write this delta G for the reaction of going liquid to solid. If this tends to go down, then this can proceed. So we've got two terms. It's like this balancing of this energy. So we went from a liquid to a liquid with a solid in it. So the energy situation changes. So we have two competing terms. One is a reduction in energy based on the fact that I have some solid form. Okay? That's 4/3 pi r cubed. That's the volume of that solid times the change in volume the change in free energy getting a solid of this volume, okay? So what we can write down here, this is reduction in energy for the solid. Now, this is going to be plus 4 pi r squared. You may remember that's the surface energy, or surface area, right? Before we had volume, here we have surface area, times gamma, and this is, gamma is the surface energy of this solid. So we're creating a new surface here. So for this phase transformation to proceed, the reduction in energy for this making a solid has to balance with how much the energy gets increased by this new surface energy, the new surface area that we produced. Okay? Now, when we do that, we've got a figure here that I'm going to show you. But here's this idea of this energy argument. Okay? If we look at the energy change as a function of how big that radius is, this is the radius of the nucleus. So if we go back to this figure here, r is right here. R is the radius of the nucleus. There's r right there. So we're going to plot this. We've got sort of two competing terms. One is this reduction in energy for the solid. So this is 4/3 pi r cubed delta GV. We've got two terms. And then the other term is this surface area or surface energy term. It does this kind of thing. It doesn't take off as fast, but it's more at the beginning. So this is 4 pi r squared times gamma. If you add these two up, you sum this situation, you get a curve that looks like this. So here's the sum. And we're going to note two things here. One is this right here, this point right here, we're going to call this r star. And this height of this energy, we're going to call delta G star. So what are these? Let's define these. Delta G star is like we're going to call this the energy barrier for solidification. And R star, we're going to call the critical nucleus size. Well, this is an energy thing. So basically what this figure is showing is once the nucleus, remember we had a little nucleus that forms, once it reaches this critical size of R star, we get over this energy hump, and now if the thing grows more, the energy can go down. That's favorable. That's good. If the radius size of a nucleus that forms is less than that, then things are going to want to shrink down, right? So here's shrink, here's grow. So what this figure is telling us is a couple things. One is we have to reach a critical nucleus size, and once we do, things continue growing. There's a figure in your book here that describes that. Okay, I mean, it talks about what we just talked about. And there's a figure in your book that talks about, this energy barrier that we've got to get over. Now, this homogeneous nucleation is when things nucleate, like in our liquid solid example, it nucleates out in the middle of the liquid or out in the middle of another phase. We're going to talk about, for a second, heterogeneous nucleation. Heterogeneous nucleation. Well, what is heterogeneous nucleation? Well, the whole idea here is we're just going to state something, and I'm going to write something, but it is much easier to nucleate on surfaces that already exist, that are already there. Now, what do I mean by that? Well, instead of this, where it nucleates here, this is homogeneous, remember? Homogeneous. This doesn't really happen very easily. What normally usually happens is this. Things nucleate on a surface that's already there. And you can see here that the surface area term is much reduced, right? The surface area of the one on the right is not as great as the one on the left. So, you know, here's the consequences here. The consequences of this are phase transformations start at grain boundaries. That's a surface that already exists. If it's a sort of a solid going to another solid, or if it's a liquid going to a solid, we could say things nucleate easier on the walls, like the walls of a mold. Let's say this is a mold I poured a liquid into, okay? It's easier to nucleate on this surface here. In fact, we can draw, and there's some figures from your book that show delta G star is lowered. That means easier nucleation. So instead of having a figure that looks like this for homogeneous nucleation, I get a figure that looks like this. And this is important in two ways. One, you can see that the critical nucleus size is smaller and our delta G star is smaller. This is hetero. Here, R star is much bigger and the energy I've got to get over is much bigger. So what that figure is showing, what that figure is showing is that it's easier to nucleate heterogeneously. Now, let me give you a practical example of this. Seeding clouds. I don't know if any of you know anything about seeding clouds. That means trying to make it rain. Well, rain means homogeneous nucleation up in the air. That means that a water droplet will nucleate from water vapor up in the air. That's kind of difficult, so sometimes we try to make it easier to rain by seeding clouds. Basically, what we do is we distribute ultrafine particles up in the air. So there's already surfaces there for the water vapor to condense on. So it's easier to make it condense. That's what they do when they do seeding clouds. Now, what you need to remember is mainly from this discussion, these two consequences. When we look at our phase transformations, in a solid, it starts at grain boundaries. From a liquid going to a solid, it starts on the mold walls, on the walls, because there's a surface already there. It doesn't start out in the liquid. That's kind of hard to do. Okay? Now, here's some curves from your book. Like we just said, it makes it easier. Heterogeneous nucleation easier. Okay, now it lowers the energy. Okay? It also raises the temperature that things can nucleate. That means it's easier. We don't have to have as much subcooling, right? This would be subcooling. Now, let's talk about one more aspect of phase transformations, and then we're going to quit on this short lecture. So we're going to talk about nucleation and growth and how they depend on temperature. It's kind of a competing effect. Okay, let's look at nucleation. So nucleation, this is more at lower temps. Okay, this is also known as subcooling. That is the driving force to change from one phase to another on, let's say, cooling or superheating. Okay, it's more the farther that you get away from the temperature. And growth, it's faster at higher temp. Now, why is that? Because most of these phase transformations that we've talked about depend on diffusion. Let's talk about the phase transformation of austenite to perlite, which is alpha and Fe3C. That's going from austenite, which has kind of a medium carbon composition, to two different phases. Both have different carbon concentrations. So diffusion of carbon has to occur. Takes a while. Now what we do is we look at, let's just look at the overall transformation rate. Transformation rate. Of our example, a liquid going to a solid. So we're going to look at temperature. So here, right there, is the solidification temperature. Okay, so that's the liquid to solid temperature right there. So basically what we just said is nucleation occurs faster, the rate is higher. The rate is higher at lower temperatures. Nucleation. Excuse me, students. Michael West. Yeah, just bring him over to my office. Yeah. Yeah, they can do that too, if they want. That's great. Bye. Okay, sorry students. Got this accepted students day. They want us to meet with some new students. Okay, now going back to here, the growth rate, because it depends on diffusion, is much higher at higher temperature. The overall transformation rate looks like this. That is, you add them both together. So here's our overall rate. And what you can see, sorry, students, what you can see is there is a place here where the rate is the fastest. There's like a sweet spot here. Dang, sorry. Okay, the rate is the fastest here. Right at that nose. They call this a nose. They call this a nose. So this curve has a nose right there. But basically there's a sweet spot. Now let's do just one figure that kind of is related to this, and then we'll quit for this lecture. So our example that we're going to look at is like, we've got a liquid going to a solid, like liquid iron going to solid iron. So let's say we're up here, we're at high temp. We're going to look at medium temp, and we're going to look at low temp. That is, how far do I subcool below the freezing temperature? Well, if I subcool only a little bit, so I'm still at higher temperature, basically what this means is, so we start with a liquid here on all these. We're going to start with a liquid. But then we're going to proceed a little further. If I'm up at high temperature, the nucleation rate is really small, so I only get a few nuclei that form, just a couple. But the growth rate is really high. So they tend to grow real fast. But there's not many of them. Okay, they grow fast. And then finally, it's all finished, all transformed. You can see the grains are actually quite large. Now here, let's go down to low temperature first. Well, at low temperature, I have lots of nucleation. See this? Lots of nucleation, but slow growth. So lots of nucleation, but they don't grow very fast. Okay, they're just growing real slow. And a little bit later, let's say they grew a little bigger. There's lots of them, like we said. So it takes a while. Now you can see that the grain size is smaller in the end than what we had above. Now it's all complete. But if I'm somewhere in the middle where I have sort of some nucleation, so I have more here, not as much as the bottom, but the growth rate is higher, then this gets finished faster. You can see the grains are kind of somewhere in between the ones in the bottom and the ones at the top. But what we want to put here is this is faster. Overall, it gets completed faster. That's like that sweet spot that we talked about. Okay, next time we're going to talk about sort of looking at the progression of these phase transformations a little more, and we're going to apply this to iron and steel.